The partition function and the consistency equation lets us now calculate further observables of the Ising model. In particular, let's have a look at the specific heat at zero external field. Now, before we start to calculate the specific heat, we should consider the mean energy of the system. The mean energy per particle is given by 1 divided by n del log z by del beta. Now, doing the partial derivative of the log, we obtain an expression in which the last term contains a factor of tanh beta h prime. Now, since we consider h is equal to 0, this has to be equal to sigma bar due to the consistency equation. Hence, the mean energy per particle is given by c half j sigma bar squared plus h times sigma bar. From here, we calculate the specific heat per particle as the derivative of the mean energy per particle by temperature, by first taking the derivative with respect to sigma bar and then taking the derivative with respect to the temperature. That leads to the expression that the specific heat per particle is given by h plus cj sigma bar del sigma bar by del T. For this last partial derivative, we use the consistency equation, reading that h bar is equal to tanh hyperbolic Tc divided by T times sigma bar. Now, assuming that we are close to Tc, meaning that sigma bar is small, Taylor expansion of the tanh hyperbolic gives us two terms: the argument of the tanh hyperbolic minus 1/3 of the argument to the power 3. Now, solving for sigma bar, we obtain sigma bar is equal to plus minus square root of 3 Tc minus T divided by T to the power 1/2, or equal to plus minus square root of 3 square root of minus tau, where tau is the reduced temperature of the system, as expressed by Tc minus T divided by Tc. From there, we obtain the partial derivative of the mean mechanization as a function of temperature, and using this result in our expression for the specific heat per particle, we see that Cv is given by 3/2 kb, independent of temperature, or proportional to the temperature to the power alpha, where the exponent alpha is equal to 0. The specific heat stays constant in the vicinity of the critical temperature. In the next step, we look for the mechanization at zero external field and how the mechanization varies with temperature. For that, we use the earlier result that sigma bar is given by plus minus square root of 3 times square root of minus t, meaning that the mean mechanization scales with the temperature to the power beta, where beta is 1/2. Hence, for temperatures smaller than Tc, the mechanization drops with the square root of the temperature. For temperatures higher than Tc, there is no mechanization. This drop-off of power of 1/2 has been found experimentally and is characteristic for Ising models in which the order parameter, in this case this is mechanization, drops off with the square root of the temperature when approaching the critical temperature. In the next step, we want to look into the field dependence of the mechanization close to the critical temperature. This will lead us to the magnetic susceptibility, a parameter that has been frequently measured. Now, first we start with the consistency equation that relates the mean mechanization, sigma bar, to the external field A. Now, solving this equation for H leads us to an inverse tangent hyperbolic of the mean mechanization, which for small mechanization is expanded in the Taylor series, finally leading to an expression how the field varies with mean mechanization. From here, we calculate the magnetic susceptibility, chi, given by del H by del sigma bar to the minus 1, which for temperatures close to Tc is about 1 divided by kBt sigma bar squared. Hence, the magnetic susceptibility scales like temperature to the power gamma, where gamma is equal to minus 1. What we just have proven is the Curie-Weiss law, saying that the mechanization of the ferromagnetic system scales like 1 divided by T. As the last example, we consider how the magnetic field close to Tc changes with internal mechanization. the dependence we obtained from the consistency equation earlier, and assuming that the temperature is close to Tc, the first term vanishes, we find that h of sigma bar is equal to kb Tc third times the mean magnetization to the power 3. Hence, the magnetic field scales with the mean magnetization to the power delta, where delta is equal to 3. Now, those exponents that we calculated have an immense importance in extended theories and are solely determined by the dimensionality of the problem and the symmetries in the problem. This is a theory that we will come across in statistical physics of the master's programs and is called the renormalization group theory, which relates the different critical exponents to each other.